please hit subscribe.
Hello friends, today we're going to compute this quantity out here. We start with a real number x, then we feed it to the sine function, then we get a value for that because the domain of sine is the whole number line, the entire real line. Then we get that value and we feed that to another sine function. Again, we get another value and we feed that again to another sine function. And we do that repeatedly. And what we're trying to find is the value to which that repeated process approaches, if any. So let's get started. We've got a three-step plan for this. The first one is to reformulate the problem using the language of limits. This way, it will be easier to talk about the problem because the language will be more precise. And also we will see that we are dealing with a sequence of numbers in this case, and we're trying to find the limit of that sequence. Then we're going to show that that limit actually exists. And this is an important step because most of the rules and the theorems that we use to compute the limit actually only work when and if the limit exists. So if the limit does not exist, we might get something from those rules, but we do not have the guarantee that that's actually the correct answer, the correct limit that we're looking for. So it's important to check that it exists. And the way we do that is we're going to show that the sequence we're looking at is bounded and that it is monotonic. We are guaranteed that the limit of that sequence exists if that sequence is both bounded and monotonic. Lastly, we're just going to compute the limit when we're satisfied that it exists. So let's start looking at the following sequence. Let's define f sub 1 of x be, let's define it to be sine of x. And so this is going to be the first number in our sequence, f sub 1 of x. Now, let's define the second number in our sequence to be f sub 2 of x, and that will just be the sine of f sub 1 of x. So sine of f sub 1 of x, which is just sine of x. So we do sine of x. Then we do that one more time to get f sub 3 of x. And we'll notice that if we count the number of applications of the sine function, that will be the same as the subscript out here. And so we can say that our f sub n of x, that's our nth term in the sequence, that will just be n times of the sine function. So we apply the sine function n times to x. And the problem now becomes, if we're going to take n arbitrarily large, does this quantity on the right approach any number? So in terms of limits, that would be, does this limit L, which is the limit as n approaches infinity of f sub n of x, does it exist? And if it does exist, what is its value? And we can now recursively define our function f of n, or rather f sub n of x, and that will be f sub 1 of x, that's going to be the first term, is sine of x, and then f sub n of x is just the sine of the previous term, and we see that here, right? F sub 3 of x is just the sine of f sub 2 of x, which is the sine of the sine of x. So these two lines here actually define our f sub n of x, our sequence, and we're out to find the limit of the sequence. And we've talked about this briefly. We can guarantee that that limit actually exists if we can show that the sequence is bounded and monotonic. So that's what we're going to do in the next slides. So boundedness. So we want to start by considering this function here, So f sub n of x is the sign of some number. So we know that this number here is something more complicated, but let's forget about what's inside, but actually consider that what we have here is just a sine function of some number inside, right? And so if that's the case, then we can be sure that this function, this term here, which is equal to sine of y, is between -1 and 1. And the reason for that is because the sine function, the range of the sine function is -1 to 1. And we know that from trigonometry. And just by showing this, we have shown that f sub n of x is actually bounded. And in fact, we know that it is between -1 and 1. And so there we go. We've shown that the sequence that we're looking at is bounded. So we only need to show next that it is monotonic. Now let's show that the sequence we're looking at, this sequence out here, is actually monotonic, and more specifically monotonic decreasing. So we're going to look at the interval where it is monotonic decreasing. Monotonic decreasing means that the term before the current term is larger. It's always larger. And the current term is always larger than the next term. And that's what we mean here, that the f sub n minus 1 is always larger or equal to f sub n. And if we look at this definition we have here of the sequence, we can actually replace f sub n with sine of f sub n minus 1. And so we do that, we get this inequality. And if you look at that more closely, what we can do is we can actually collapse f sub n minus 1 of x into just theta. And so we have this inequality. We just have to show this inequality then. And if we look at the definition of the sine function from trigonometry, we see that the sine function is actually this vertical distance from this point here, this point being on the circle with radius 1, making an angle theta from the x-axis here, positive x-axis. That vertical distance is sine theta by definition, and that arc length is theta by definition. So it looks like that on this first quadrant, that's theta equals 0 to pi over 2, we always have theta to be greater than or equal to sine theta. And that shows that our sequence, if our x is between 0 and pi over 2, our sequence is actually monotonic decreasing. Now, we're not going to show it here, but if we have an x that is in the interval from 0 to negative pi over 2, this bit here, we're going to have a monotonic increasing function. If you want more details on that, you'll have to look at the link that I put in the description. I write there in more detail about this bit of the problem. And for the purposes of this video, we're just gonna show that, or actually we have shown that this function that we're looking at is monotonic decreasing. So now that we've shown that it's monotonic and we've shown that it's bounded, we can actually start computing for the limit. We start with this statement. So this is just the same as this one here. Then we replace f sub n with its definition here, recursive definition. So that's in terms of f sub n minus 1. Then we know that sine is a continuous function, and so we can put the limit inside the sine function. And so we're just moving this bit here into this bit here inside the brackets. Now, what we have here is the limit of f sub n as n approaches infinity. But as n approaches infinity, we also have n minus 1 approaching infinity. And so this is basically just L as well. And so we're left with the following: L equals sine of L. And we just have to find that value L. Now, you might be asking, because sine is periodic, it's possible that we have multiple values of L, so multiple limits, and that doesn't make sense, right? If you have multiple limits of something, then you don't really have that limit. But we can show that in the interval that we're looking at, or for any value of the starting variable x, for any value of that, it can be shown that we will always have sine of x to be in the interval -1 and 1, and more precisely in the interval 0 to 1 it's decreasing, and in the interval 0 to -1 it's increasing. And so because it is monotonic in that interval, in those intervals, we can say that there is a one-to-one, it's a one-to-one function. That is, L to sine of L is 1-to-1, meaning if you give it an L, there's only one possible value of sine of L. And if you have a sine of L, there's only one possible value of L. So that's a one-to-one function. And you can look that up in the details in the link that I put below in the description. But suppose you accept that already. Now we just have to guess or find a value for L. Now if we just examine that, think about the common values of L. It's not going to take us long before we realize that actually 0 satisfies this. So if you have 0 here, sine of 0 equals 0. And because we have shown that this is just 1-to-1, because this is just a one-to-one function because it is monotonic, then we can be sure that there is only one value, and that value is 0. And so that L that we're looking for is in fact 0. What that means is that whatever number we start with for x, if we do the process of repeatedly applying the sine function, we're always gonna get closer and closer to 0, whatever value we start for x. So that's what we've got for today. If you're interested in a more detailed solution, please check out the link that I put in the description. And if you learned anything from this video, please do help my channel by clicking the subscribe button and the notification bell. See ya!
Please hit subscribe.